Okay, so simple harmonic motion, why do we care? 3 reasons. Well, 4 really, I guess. Number 1, it's going to be on the AP exam. That's reason enough. Number 2, it's easy to model, meaning math or equation. So we can model simple harmonic motion. We can make predictions about where the oscillator will be at any given time, what its velocity will be, what its acceleration is going to be, what the energy in the system will be, etc. And we're going to be exposed to all that. And I guess this is going to be extremely intimidating, and we're not really going to do that much with it, but you should know what I mean by that. So, for example, to determine where our oscillator is, let's see, oh, I already threw it away. So we have that object going back and forth along, let's just say, assume it was an x-axis, and we can know exactly where it was at any given time t using this equation, and it is a cosine function, and it's going to freak you out, but here it is, and it's not that complicated. We'll go over it later. So something called A, which stands for the amplitude, times the cosine of, okay, hold on, it's not as bad as it looks, 2 pi over the period, all that stuff, which is a constant for any oscillating system, times some time t is how we get the position. So even though that looks kind of intimidating, that is actually something that is very easy to model. So that's that's why we care about simple harmonic motion. One reason is because we can model it. Other examples of oscillatory motion are too complicated for us to deal with. And the amazing thing is that many things that oscillate, vibrate, wiggle, etc., do so in simple harmonic motion. So it's not only I'm going to be on the AP exam, it's easy to model, and it's many things are in simple harmonic motion when you disturb them from their rest position. Okay, let's introduce the 2 simple harmonic oscillators that we're going to deal with, and they are as follows. We have our spring mass oscillator. Okay, well, as the name implies, there's going to be a spring and there's going to be a mass attached to it. Now you say, well, okay, there's very few things out there in nature that look exactly like that. But that's okay, because there are many things that have mass and are spring-like in nature, i.e. almost everything to a certain degree or another. Okay, some of the features of our spring mass oscillator is, okay, we really only put this surface here on the bottom to kind of give you a sense of, well, what is this mass sitting on? We don't, we could leave it out, but it's really there just to kind of keep you from wondering, why is this thing not falling down? So, but we're going to make it mu equals 0, and hopefully you realize that means no friction here. We're also going to, and there's going to be a K in our simple harmonic oscillator, spring mass oscillator. The spring is going to have some K value, and hopefully you recall that that's basically the symbol for the spring constant, which is in turn a constant of proportionality that indicates the stiffness of the spring. And since we're talking about that, let's just go ahead and remind ourselves, okay, well, where did that come from again? And let's move this up here. Okay, so when we talked about springs and Hooke's law, and we talked about this, we did a little bit of this with, get over. So here is our spring force, and here is our spring stretch or squish. And what we see is, and this is an ideal spring, and obviously, and this is going to be an ideal spring. So basically, the spring constant is the slope of that spring force versus stretch or squish graph. So I guess we should also mention that about our spring. It's going to be ideal. It's already understood. And that just means an ideal spring is one that follows Hooke's law. Okay, what else about the spring? Okay, it's going to be massless. You say there's no such thing as a massless spring. I agree. This is called a simplification of reality. This is called a model. And our spring mass oscillator, we're going to assume that all of the mass of the oscillator is tied up in the mass and none of it is in the spring. Because if you were to start doing that, that's, I don't know, that's graduate level physics to kind of model that. So, okay, so we're not going to worry about it. Plus, go back here, many things can be modeled using just this simple spring mass oscillator. Okay, let's see. What else? That's it for that. Let's move on to our other one. The other harmonic oscillator is going to be something that you're also pretty familiar with, and that is a simple pendulum. Okay, what makes it simple? A simple pendulum is when all of the mass, I don't know if I want to put this in here. It's not a big deal. Anything on the AP exam is going to assume to be a simple pendulum. But if you're curious, what makes a simple pendulum is all of the mass is in the bob. And the bob is just the thing at the bottom. Don't ask me why it's called a bob. Okay, so basically you're pretty familiar with pendulums from our unit on energy. And so what we're going to do is we're going to disturb our pendulum from its equilibrium or rest position. And you know what that means. We're going to put energy into it, but we're going to basically bring it up some angle theta, and we're going to see that this thing oscillates back and forth, and it can move or it can oscillate in simple harmonic motion if, and we're going to go over this later, and it's not a huge deal, but if the angle is small enough. Okay, because when you start getting the angle, which would really be the amplitude, too far, it will be oscillatory motion. But we can no longer consider that the restoring force is linear. When this angle is small enough, the restoring force increases as you pull it back in a linear fashion. Okay, and what is small enough? Okay, our first kind of mention of even radians, the angle is small enough if it is less than about, I think it's pi over 8, I think. We'll talk more about that later. Okay, these are your spring mass oscillators.